this week I'll try to cover up with the missed classes. So in the last class, we had okay. In the last class, we had discussed the initial half part of the unit 2. We have discussed about what is automated production lines, what are the different configurations in automated production lines. We discussed about uh, what are the different work part transfer systems. We came across the synchronous or synchronous type. Then we have studied the different work part transfer mechanisms, wherein we have studied the linear and the rotary type. We have seen different examples under linear transfer mechanisms and rotary transfer mechanisms. And to be specific, we have studied in detail about the walking wheel mechanism and the Geneva wheel mechanism. And we have solved a couple of problems under the Geneva wheel mechanism, which are very simple problems, yet important. After that, we discussed what is storage buffer, and then we discussed about the different control functions. So today we will start with analysis of transfer lines. This part, as I said, is having problems that we have to solve. So before we proceed to solving the problems, we first need to know what are the different equations that we will be using in order to solve the problem. Can you all hear me clearly?
Yes, ma'am.
Okay. So what is this analysis of transfer line? Yeah. So basically what happens in the analysis and design of automated production line, there are these three problem areas which must be considered. Okay. And which are those three problem areas? They are as follows. One is line balancing. Next is the processing technology. And then we have the system reliability. Okay. When it comes to these three problems that we encounter in this automated production line, the third one, that is system reliability, that is of our concern. Our complete discussion after this, in this unit basically, is going to be with respect to the system reliability problem. Okay, but before we proceed to what is the system reliability problem and how we can deal with it, we shall quickly see what are these line balancing and processing technology related problems. One second. Okay, so moving on to the first one, that is the line balancing problem. We being in the second unit of our syllabus, we haven't still come across this line balancing. When we proceed to the third unit, that is on manual assembly lines or the automated assembly lines, in that we will come across this word line balancing. Now, what do we mean by line balancing? This word basically, line balancing, it is closely associated with manual assembly lines. Okay, and this problem, it can also be seen in automated production lines. Therefore, it is considered as one of the problems in automated production lines here. When it comes to line balancing, what we mean by that is whatever is the total processing work that we need to perform on an automated line, it has to be divided evenly as possible among all the workstations. Line balancing. Okay. So here, whatever is the work that you have to do on a certain part, okay, in order to convert it from a raw material to a finished part, all the work that has to be done, uh, it is said that it has to be evenly distributed at all the stations that are there on the line. Okay. So suppose if you consider the manual assembly line, the total work that has to be done, it can be divided into smaller work elements. Like at every station, there will be little assembly work done, and then it is forwarded to the next station. So all the sub assemblies that are there, they go on getting assembled to get the final assembly. Okay, so that's very much convenient with respect to the manual assembly lines. Okay, assembly is just different and production lines are different. So when it comes to an automated production line, uh, there are these different processing steps that need to be performed on the part as it moves from one station to other station. Okay, and what happens? There will be some constraints that come into picture whenever we go for these processing operations. For example, suppose if you have a transfer line and in the part that is there, there has to be a threaded hole that has to be made on that particular part. So when I want to have a threaded hole, what has to be done? Initially, drilling must be done, and then after drilling, tapping operation has to be done, right? So in order to get a threaded hole, there are these preceding operations that need to be performed, and only then you can proceed to go for the or you can proceed in order to get the threaded holes. So the precedence constraints are that which come into picture on a production line. So the precedent constraints, they basically impose some kind of restriction in order in which the processing steps can be carried out. So you just cannot at random go for any operation to be performed. There has to be a certain sequence that has to be followed in order to perform the required task on that particular part. So once the sequence of operations is established, then there is a service time, which is at the given station. Every station is going to have its own service time, right? The actual cycle time or actual time which it takes in order to process that particular part. So once you decide as to what will be the sequence of operation, then the service time at the given station, it will depend upon how long it takes to accomplish the operation at that particular station. So this is one of the problem that we have with respect to automated production lines, that is this line balancing problem. Okay, and then moving on to the processing technology. Now, whenever it comes to processing any of the part, okay, there is so much that you need to know about the part, maybe the raw material. If you consider a raw material, you should know about the metallurgy of that raw material. You should know what is the machinability of that particular material, what type of cutting tool is required, at what speed the workpiece, the raw material can be machined, what will be the feed, how the chips can be controlled. And there are so many other issues with respect to the material alone. So when we talk about the process technology, here we refer to the knowledge about the different theories and the principles about the particular manufacturing process that you're going to use on the production line. Maybe about the manufacturing process, maybe about the raw material. Okay, all of these things should be known very much in detail so that any problem that is encountered while you go for the machining operations, they can be solved by direct application of good principles, like the machining principles. So when you very well know about what are the different theories, the principles that are associated with the different production operations with respect to different materials, it becomes easy to tackle all the problems that will be encountered when you actually start the machining process. Okay, so in each process, there are these new technologies that have been developed over a number of years with lots of research and development, with lots of practice. So by making use of this technology or the technologies that are available at every individual station in the production line, we can try to achieve maximum performance by knowing all the details about the different processes that we are using. So that's how you can deal with the other problem, that is the processing technology. Now coming to the point of our concern, that is the system reliability. So system reliability problem is the primary focus here, and it can be divided into two parts. So before we proceed to what are the two subdivisions under system reliability. Let's just I'll just brief you about this third problem that we face, that is the problem of reliability. What happens is, if when we talk about an automated production line, it's not going to be very simple. Okay, there is so much of complexity. There is so many integrated systems that are at place in an automated production line. So if you can just imagine, if even one workstation stops for any reason, the entire system is going to come to halt. Okay, so things are going to be very much complicated and complex when even one single station breaks down for any reason. The reason for breakdown are so many. I'll discuss the reasons as and when we proceed. But then the reliability here is very important because we have all the workstations, the material transport systems, all of these things are integrated. So we have to be very careful with respect to the reliability of the system. Okay, so here basically the system reliability problem here, it is divided into two parts. So we are going to analyze the transfer line with no internal part storage. What do I mean by internal part storage? It's nothing but a buffer storage station. So we have already discussed about what is the buffer storage station. We have discussed that it is a location in between different stations, workstations. It can either be in between two stations or it can be after a set of stations like stages. So if you have a storage buffer, then there are so many problems that we can prevent. Basically, the problems with respect to blocking and starving of stations. So we will have the analysis of transfer line with no internal part storage, and we will see the analysis of transfer line with internal part storage buffer. So we are going to consider these two conditions, wherein we consider a transfer line which has part storage or the buffer storage stations in place. And then there is this another condition wherein we do not have the internal storage buffers in place. Okay, so the second condition that we see, the analysis of transfer line with, the first condition that we see, the analysis of transfer line with no internal part storage, it is nothing but your regular, the conventional automated production line that we have already seen. Okay. So let us start with the first one, and I just want you all to have a page, a book and a pen in front of you because we will start writing the equations, which are very important. So you all can just write down under the main topic analysis of transfer lines. Under that, you can write the first one, that is analysis of transfer line with no internal part storage. And the second case we are studying is analysis of transfer line with internal part storage or storage buffer. So just write down this, and then you can just start writing the thing under the first topic, that is transfer lines with no internal part storage. Okay, so I'll just proceed now. So these are some of the assumptions about the operations of these systems. So what happens is we are going to develop this mathematical model now. Okay, we are developing mathematical models, and these models that we will be developing can be applicable even to the rotary indexing machine. Okay, and so to proceed with, we first need to make these few assumptions regarding the operations of these systems. So just write down these assumptions as I put them on the presentation here. The first assumption that we make here is that the workstations perform processing operations such as machining and not assembly. So we are talking about automated production lines, and therefore we assume that every operation that is performed here is going to be related to the processing operations, or maybe machining or any other type of processing operation.
Excuse me, ma'am.
Yes,
Ma'am, the slide is not changing.
it's not changed.
No, ma'am.
Now?
No, ma'am. It's not changing. Y- Yes, 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 ma'am. Now
Now
it's
is it
changing.
visible?
Yes, ma'am.
See now?
No, ma'am. It's the same slide now.
I had put the same slide. Now it's the new slide. I mean, the second
No,
slide.
ma'am. No, ma'am. It's not visible. Yes, ma'am. It's visible now.
Shall I proceed? Shall I proceed?
Yes, ma'am.
Tell me, can you hear?
Yes, ma'am. Continue.
Just a second. There is this overlapping that is happening. Okay, can you hear me?
Yes, ma'am. But it's you're echoing, ma'am.
That's what is happening. Now,
No, ma'am. Still echoing.
can you see the slide?
No, ma'am.
Audible?
Yes, ma'am. But echoing.
Am I audible? Still echoing.
Yes, ma'am.
Clearly audible or echoing?
No, ma'am. Still echoing.
Hello? Echo. Hello? Hello?
Ma'am, it's echoing.
Just hold a minute. हे करा बंद करा मीटिंग मी कॅन्सल करा कॅन्सल कट करा हां मी मायक्रोफोन अलाउ केला ओके am I no it's still going am I audible echo
Ma'am, there are two logins of yours. I guess you have to end one.
no I don't have my mobile login it's only one you इथे रिटर्न रिजॉइन म्हणू नका आणि तिकडे जाऊ नवीन याच्यात इथं जा क्लास वर्क मध्ये जाऊन आणि हे करा मीट आता कसं त्यांनी यायला पाहिजे आणि थांबा डोंट अलाव म्हणा बघूया अलाव केलं की जॉईन कर हां जॉईन करा ओके एम आय ऑडिबल
Yes, ma'am.
echo
No, ma'am.
sure na there is no echo because
Ma'am, there is very slight echo going on.
Ma'am, it's okay.
see am I audible
okay now?
so there's a lot of echo
Ma'am, it's little echo.
it's echo
Again?
there is echo right
No, ma'am. It's very
This
little.
is all right.
Okay, continue.
okay you can hear me clearly right
Yes, ma'am.
you can see the slide also yes
No, ma'am. No, ma'am. Slide is not visible.
sorry I didn't start with this now
Yes, ma'am.
okay so we will just discussing about the transfer line with no internal part storage. So before we understand the different mathematical models involved here, we are going to see certain assumptions that we make at start. Initially, the first assumption here is that the workstations, they perform processing operations such as machining and not assembly. Again, this confusion, this assumption basically is made because you have similar analysis made with respect to assembly lines also. So here, when it comes to unit 2 and when we are talking about the automated production lines, we assume that all the operations that are performed here are related to machining and not assembly. So the next assumption that we have here is the processing time at each station is constant, though it not necessarily be equal. Okay, so understand the difference between constant and equal. They are not the same. Constant processing time is what we assume. Maybe the processing time may not be equal at every station. It may be different at every station, but it will be constant for every part that comes in for the processing operation. The third assumption that we have here is the work part transport is synchronous. So every work part transfer that is taking place from one station to another station is all happening synchronously. That is another assumption. And the last assumption, there is no internal storage buffer. So these are the four assumptions. Kindly note down these assumptions. As we have started late, I'll not take a break, okay? We will stop the class at 1:30. Have you noted down the assumptions?
Ma'am, 2 minutes.
Yeah.
Done, ma'am.
Okay. So in order to proceed with the different mathematical models, initially we should know what is the cycle time. So we'll just see what is the cycle time analysis here. The meaning of cycle time remains the same in throughout this computer integrated manufacturing. It will not change. Cycle time means the same in the first unit, second unit, and so on. So what happens is in the operation of an automated production line, the parts, they are going to be introduced first in the first workstation, and then they will be proceeded or transferred to the other workstations which are in a sequence. Okay, and there is going to be this fixed interval of time for which they will be held at a certain workstation, and there is some time which it will take to move from one station to another station. So this particular interval, this defines the ideal cycle time, that is TC, of the production line. So in the operation of an automated production line, parts are introduced into the first workstation and are processed and transported at regular intervals to the succeeding stations. So this interval, it basically defines the ideal cycle time, that is TC, of the production line. And TC in the processing time for the slowest station on the line plus the transfer time. So this is the equation for TC. We have max of TSI plus TR, where these are the following terms.
Ma'am, slide
TC,
is not changed. Yes, ma'am.
now,
Yes, ma'am. Visible.
okay. The complete slide is visible, no? Cycle time analysis.
Yes, ma'am. Cycle time analysis visible.
Okay. Just note down this equation of TC, where we know TC, it is the ideal cycle time on the line. TSI, it is processing time at station, and TR is the transfer time, or we also call it as the repositioning time. Please note down the units correctly.
Yes, ma'am.
Okay. So here basically in this equation, we see that we have used the term max of TSI, that is the maximum processing time in the line. It is because we consider the bottleneck station here, which usually decides the pace of the production line. So until and unless that bottleneck station time is not considered, any other station which takes less time will not really make any difference. So we are basically concentrating on that station which is taking the maximum time, that is the bottleneck station. So we have used the term max of T subscript SI, which defines nothing but the processing time at the bottleneck station. Whereas the remaining stations, they will have smaller service time, which must wait until this bottleneck station completes its operation on it. This kind of situation you will also see in the manual assembly lines. So in the operation of a transfer line, random breakdowns and planned stoppages cause downtime on the line. So what happens is we assume that okay, all the things are going to go as planned, okay, but then there are these certain breakdowns that you will experience whenever you actually start working. So whenever there is this manufacturer who tries to sell any of his machines, they all claim with 100% efficiency. They say that okay, this particular machine is having so much of production rate, or say whatever. They are going to give all their terms, and their performance measures are going to be based with 100% efficiency. But in actual practice, if you see, that is not possible. There are so many breakdowns that can happen. There are number of reasons for a breakdown, or the machine gets some maintenance work. There is some unexpected breakdown stoppages that we experience. So in the operation of a transfer line also we will experience the same. There will be these random breakdowns or maybe there are these planned stoppages which will cause a downtime on the line. Now, what do I mean by downtime? Downtime is the time for which the machine is down in the sense it's not performing its task. Okay, and uptime, there is another word which will be coming across, uptime. Uptime is the time for which the machine is actually performing its task, and downtime is the time for which the machine is actually not performing. Okay, so understand this difference. So there are these common reasons for downtime on an automated production line. Um, so there are these reasons. We'll discuss about those reasons. But what happens? Although these breakdowns or the line stoppages occur randomly, their frequency can be measured over a long run. So frequency of breakdown that is going to happen in the production line, it can be measured. We can actually measure the frequency of this breakdown. Okay, so when the line stops, it is down for a certain amount of time. Okay, so downtime occurrences, they usually cause the average production cycle time of the line to be longer than the ideal cycle time. So we have just written what is TC. TC, we have considered everything to be going smoothly, and therefore we term it as the ideal cycle time. But in actual practice, we do not always achieve that ideal cycle time. We have this average production cycle time that we come across. So as I said, there are a number of reasons for this breakdown on an automated production line. And what are those? One reason could be there is this power cut, power failure. There can be some worker breaks, okay, that the workers are taking. That can be a reason. There can be this mechanical failure of the workstation, or maybe there is a mechanical failure of the transfer system itself. Maybe there is this tool failure at the workstation. There's some tool breakage that happens, or there is time that is going to be spent, or the machine is going to be stopped for some tool adjustments, or there may be some electrical malfunctioning that is happening, and maybe there is some preventive maintenance that has to be done online, so you're going to have a planned stoppage. Okay, so there are so many reasons that, and these are some of the common reasons for the downtime on any of the automated production lines. Okay, so as I said, there is this ideal cycle time, and then there is this actual or the average production cycle time. So here, when the line stops, it is down for a certain amount of time for each downtime occurrence. Downtime occurrence causes the actual average production time of the line to be longer than the ideal cycle time. So expected ideal cycle time says 5 minutes, but because of all these breakdowns, unexpected or random breakdowns, the cycle time will then be increased. So basically all this downtime that happens, it is going to add on to the ideal cycle time. It will not be as expected, but it will take more time. So we can formulate the following expression for the actual average production time, that is TP. And this is the equation for TP, that is TC plus F into.
Ma'am, the slide is not changed. Yes, ma'am.
Now,
Yes, ma'am.
okay. So just write down this equation for the actual average production time, TP. So here in this equation of actual average production time, we know TC. We already know what is TC. TC is nothing but the cycle time. We have F and TD, these are the new terms that we have just seen. Where F, capital F, it is the downtime frequency. That is number of times the line will stop in a cycle. Okay. And TD, it is the average downtime per line stops. So frequency, that is number of times there will be this line stoppage, and the time for which the workstation or say the line completely stops. That will be in minutes. That is TD. So what does this downtime basically include is it includes the time for repair crew to swing into action, diagnose the cause of the failure, then fix it, restart. All of this time is included in TD, that is the downtime. So you can say TD is the time from which there is this breakdown happened till it restarts everything. Maybe the system is kept ideal till you get somebody to fix it. Okay, after the person comes, he repairs it, he puts it back into action. All of that time is going to be counted as the downtime. Okay, so we have this product F into TD that you can see F into TD. It is the downtime averaged on a per cycle basis. Okay, have you noted this?
Yes, ma'am. Done.
Is the next slide visible?
Yes, ma'am. No,
Yes.
no, ma'am, not visible.
Visible now?
No, ma'am.
Now?
Yes, ma'am.
Okay, since all the workstations on an automated production line without internal storage are interdependent, the failure of one station can cause the entire line to stop. So this is our concern here. When we talk about an automated production line, where all the workstations, all the transfer systems are all integrated, they are they are dependent on each other basically. So what happens even if one workstation or one transfer system is going to fail, the entire line is going to be stopped. Okay. So so let us now write this. Here you can just note down two things. After you have written the average production time TP, no, just write down this point as there are two types of approaches that will come across here. One is called as the upper bound approach, and the other one is called as the lower bound approach. Okay, so this particular thing that you see here, let pi be the probability or frequency of a failure at station I. Just note down this, where I indicates the stations and n indicates the number of workstations on the production line. Okay, so before you start writing let PIB, write it as the upper bound approach, upper BOUND, upper bound approach. So there are these two types of approaches that we have, the upper bound and the lower bound approach. So what happens here is whenever a workstation breaks down, okay, there are these two possibilities of analysis. Like there are these two possibilities basically, whether the work part, okay, it is removed from the transfer line or it is going to remain on that transfer line. So I'll repeat again. We are talking about two approaches here when it comes to analysis of automated transfer lines without a storage buffer. we again encounter these two situations. We call them as, or these are the two approaches that we have. One is called as the upper bound approach, and the other one is called as the lower bound approach. Okay, and that depends upon whether the part is removed from the workstation whenever it fails. Sorry, whenever there is a breakdown. Suppose if the part is removed from that station, then it is said to be the lower bound approach. And whenever the part is still on the station, okay, or it just moves to the next station, then it is said to be the upper bound approach. So just write down here, there are two types of approaches, that is upper bound approach and the lower bound approach. Can you see this? Can you see this?
The slide is visible, ma'am.
Not the slide. I've just put up a PDF here, analysis of automated transfer lines without storage during breakdown. Upper
No,
bound
ma'am.
and
No,
lower bound approach.
no, ma'am. Only the slide is visible.
Okay, fine.
Ma'am, your presentation is not visible.
Yeah, I have I'm just trying to switch it to some other PDF that I need to show here in order to explain the upper bound and the lower bound approach. But there is some network issue again. Just a second.
It is visible, ma'am.
Hello, am I audible now?
Yes, ma'am.
Okay. What screen is visible to you all? Is the PDF visible or it's the presentation that is visible or
Ma'am,
none?
nothing is visible now.
Okay, is the screen visible?
Yes, ma'am.
Or can you see this upper bound and lower bound approach?
No, ma'am. Only the screen, your computer screen is visible. The PDF is not yet visible.
Now,
No, ma'am.
okay. What about this presentation? Is it visible?
No, ma'am, not yet.
Okay. There is something, I don't know what's going wrong today. I'm using a different system, maybe. This is bad, I don't know. Anyways, I'll continue with the presentation itself. Now, is the presentation visible?
No, ma'am. Presentation is not visible.
What is visible then?
Your computer screen is visible, ma'am. The files, this PC downloads.
Can you see the PDF now?
No, ma'am. PDF is not yet opened.
Then what you can see?
Just your screen is visible.
Uh, now?
Yes, ma'am. Now it's visible. Now
Not
it,
clear yet,
yeah.
no?
Yeah, no, ma'am. It's like
It's
it's blinking.
flickering.
It's blinking. Yeah.
Okay, we'll stop here. I'm unable to get it. I don't have the present now option on this coming up. Am I audible?
Yes, ma'am. Yes, yes.
Okay, Thursday I have a class, right? At what time? At 2 o'clock?
2:30, ma'am. You have a class at 2:30.
2:30.
Yes.
And after that, you all are free. So we'll have a 2 hours class on Thursday. And that is, I'll take one, I'll extend the class.
Okay, okay, ma'am. Yeah.
Okay.
Yes,
And
ma'am.
maybe on Friday also, I have a class, and I think you all are available.
Yes, ma'am.
So we will have an extra class as well on Friday. I'm so sorry about this thing today. I don't know what went wrong. I'm unable to share it only now. I'm unable to share the screen.
Okay,
Uh,
ma'am.
so anyways, I'll again put all the PDF content also in the presentation, and I'll show it as a presentation only in the next class. And by this week, we will finish off with this unit. I need another 3, 4, maybe 3, 4 hours is sufficient for me to finish this unit. So we will